Now let's get started. Hi everyone, my name is Megan. I'm from Los Alamos National Lab. And I'm part of the Trolley Cloud team, and this is my pink presentation on kernel security, but specifically how does Trolley Cloud stand privilege and why you should too. Just for a bit of background about myself, so I am a Trolley Cloud developer, but I also do user support on all of Los Alamos' supercomputers, which will make more sense later in the slides about why that's important, but just for a bit of context. First, I'd like to acknowledge the current Trolley Cloud team and everyone's very unique headshots. So kind of first we'll go into kernel self-protection. Pretty briefly, I think you mostly know how the kernel security works, and then I'll kind of jump into what Trolley Cloud does to make security things as easy as possible for us. So what is kernel self-protection? So this is just a little snippet from the Linux kernel documentation that I really liked. So kernel self-protection is the design and implementation of systems and structures within the Linux kernel to protect against security flaws in the kernel itself. So some goals of kernel self-protection are to be effective, on by default, to require no opt-in by developers, have no performance impact, have no impact on kernel debugging, and have tests. So some pros of this is first, lots of very smart people's time, effort, energy has gone into the kernel self-protection, so lots of effort that way. And also it is very widely used, so lots of eyes are watching it, so if there is an issue, it's pretty easy to get caught compared to other software. Writing secure privilege programming. It's terrible, to be very honest, but just to remind you how awful it is, here is just some of the few rules and warnings you have to follow when writing secure privilege programs. So you need to hold privileges only when required, drop privileges when they won't be required again, to drop privileges before executing another program, don't run a shell with privilege, close all unnecessary file descriptors before an exec, watch out for signals and risk conditions, and so much more. I don't know about you, but I will not remember all of these rules as long as all the other Los Alamos security rules, so I don't want to deal with that, so that kind of jumps into what Trolley Cloud does to avoid writing secure privilege programming. So what is Trolley Cloud? So it is a lightweight, fully unprivileged container implementation that's developed at Los Alamos specifically with HPC applications in mind. So kind of important, why do we need to run 100% unprivileged? First up, our user base will never have privileged access on the HPC systems. They will never get that. Also, we need to support secure computing at multiple levels. So that means we have to support our classified computing with all their secret stuff that no one can look at. Also need to be very careful about our secure computing even in the open. So these are our Trolley Cloud philosophies. So the first one is to be transparent, not opaque. Next is to be simple, not complex. And the third one, which is the one we'll focus on here, is to trust the kernel. So within trust the kernel, what we mean by that is we don't maintain a security boundary. We stay in privilege and avoid responsibility. The third one's very important because when there is a security issue, since I do user support, I'm the one people talk to, and those conversations are terrible. So I like to avoid having to have those conversations with users, especially having to deal with the incident that Jane talked about earlier today. So kind of wrap everything up. So how does Trolley Cloud stand privilege? Just by distro tools, expecting privilege. So I kind of talked about this for those that can't apply, so you might kind of recognize this material. So we use root emulation. So why do we need root emulation? As I said before, HPC users do not have root access on these clusters, but we need to check the programs that we do have root access even though we are completely unprivileged. We do that by mapping the EUID and EGID to 0 inside the container. So this is the example we'll use for the next couple of slides. So DNF-y install OpenSSH cannot be installed without root emulation because it needs root access because it's shown, and also lots of other packages depend on it as well. So with the root emulation mode, our current implementation uses setcomp, so I'll kind of briefly explain that. So setcomp stands for secure computing, which I don't think is a particularly great name, but what it does, it manipulates the system calls that a process may take. So how we use setcomp with our root emulation is we first construct a fixed syscall filter by writing a BPF program that does nothing and returns success. We install said filter with PRCTL, and then all Docker run instructions go through said filter. For my visual learners, this is what this little diagram will go through. So this is our example Docker file, pretty bare bones. So first up we have just basic from Linux 8, non-run instructions we kind of ignore in the context of the filter. Then we have run gnf-y install OpenSSH, run instruction, they'll go through the filter, but specifically it is the chown2 syscall. They'll go through a filter which does nothing and returns success, and then it works. Just to really prove that it works, I'll go through some examples. So this is, there we go. We are building that image, but we're using strace to kind of show what's happening under the hood a bit more. So first, we are opening SSH key sign, file descriptor 49. We are writing to it, still writing to it, close the file, get the UID, but now we've shown it errors and it does not work. It has an invalid argument. Go. So here is the exact same command, except this time we are using our setconf filter for root emulation. So you can see here, same thing, opening SSH key sign, file descriptor 49, writing, closing, get the UID, and now it works, and that's happy. This is a very brief explanation, but our code's open source if you do want to take a deep dive. We also have a paper that we just submitted to PERC, so I included the link to the preprint paper there. Yeah, that's pretty much it. I did want to include, so I said before, we are open source. We're on GitHub if you want to look closer at the code. We also are trying to get some more user engagement, so we have a low traffic mailing list with groups.io, as well as a Charlie Cloud channel in the HPC container Slack, with a Charlie Cloud user group meeting the first Tuesday of the month. Yes. And that's all I have. I don't know if there's any questions.